This problem says, find the local extrema of f of x equals x cubed plus 3 over x. Then, describe intervals where f of x is increasing or decreasing. And finally, sketch the graph of f of x. So for the first part, how do you find the local extrema? Well, we haven't been given a boundary, a set of values to stay in, so you probably have to consider all of them on the x-axis. But what is the technique? What does it have to do with the first derivative? Why don't we take the derivative right here? So let's start with f of x. Let's erase these parts right here. So we can rewrite this function as x cubed plus 3x to the negative first, right? Now we want to find f prime of x. This is nice. We can just use the power rule. So this would be 3x squared and negative 3x negative 2. So it would be minus 3x negative 2. And how is the first derivative related to the extrema? If you remember from textbooks that you've been using or classes you've been taking, we find the critical numbers, which are where the first derivative is either 0 or we also need to pay attention to where it's non-differentiable, meaning the first derivative is not defined. But we can do some factoring here. What can we factor out right here? How about if we factor out 3x to the negative 2? Now, if you factor a 3 out of here, it's just x. If you factor a negative 2 out of x squared, this would be x to the 4th, right? Minus, and this is the same thing. So we actually got a difference of squares here, don't we? What would this be equal to? 3x to the negative 2. Now, if we consider this x squared squared minus 1 squared, you know, the difference of squares is this would be x squared plus 1, x squared minus 1. And what do we have here again? Another difference of squares. What would this be? Well, we've got 3x to the negative 2. This is the same. This is x squared plus 1. And how about this? This would be x plus 1, x minus 1. So, critical numbers. And then we'll decide whether or not they are extrema. Well, this function would not be defined at x equals 0 because 0 squared is 0 and 0 in a denominator with a negative exponent. This would lead to division by 0. So we know that this is a point where it's undifferentiable. How about these? How about this? Can this factor ever be 0? No, because x squared is always positive or 0. And if you add 1, this is always going to be positive. I can put a positive right here. This is also going to be positive when it's not 0 because 3 over x squared, well, the x squared is always going to be positive. How about this one? When is this 0? with making the whole thing 0 when x is -1. And when is this 0? When x is 1. So here are 3, and these two, if x is 1 or -1, this first derivative is going to be defined. So these would be stationary points, where the derivative, where the tangent line is horizontal. Now, if you've got a point on a function where there's a local maximum, the function would look like this. If you got a local minimum, it would look like this. And at these maxima and minima, the tangent would be horizontal, or the slope of the tangent would be 0. Consider the points right below, or x value slightly less than the stationary point. Look, if the slope is positive, then the value of the derivative is positive. And then right after the maximum, it starts going down so that the derivative is negative. So what you can do is you can tell if you've plugged in a value here and the value of the derivative is positive right before that and negative right after that, then you know. So if you've got positive, 0, and then negative, you're talking about a maximum. If you've got a negative slope, then a 0 slope, and then a positive, you're talking about a minimum. So let's consider points slightly less than -1 here. Well, this is going to be a positive value, so we don't need to worry about. But this is going to be a positive value. If it's slightly less than -1, like -1.1, this will be negative. And if this is slightly less than -1, -1.1 minus 1, this would be also negative. So this would be positive. So we're already looking towards this, and we know at -1 is this. Let's double check and make sure. Let's consider a value slightly greater than -1, say -0.9. Well, this would be positive because -0.9 plus 1 is like 1 minus 0.9. This would be a very small but positive value. -0.9 minus 1 would be another negative value. So there we go. -1, because it is a place where the tangent is horizontal, and right before it, the slope is positive, and then right after it, slope is negative, where this would be a local maximum. Let's check for the value 1. If a 1 is here or here, it's always going to be positive. But we want to check right before this point. So let's say right before 1, so like 0.9. This would be 0.9 plus 1, this would be positive. But 0.9 minus 1, this would be negative. So we're looking at this, and then at 1, it's this. Now let's think of a value close to but slightly greater than 1, 1.1. 1.1 plus 1 is positive. 1.1 minus 1 is a small positive number. So it's positive. So this would be a local minimum. So if the theory goes that you can only find local extrema at places where you have a critical number, and if you use the first derivative test as we did right here, we can say that we've got a max at x equals -1, and a min at x equals 1. Now, it could be, sometimes you have a function that looks like this. I'll draw a piece of it, where the derivative from this side is 1's tangent with a certain slope, and then the derivative of the same point from the other side is a different slope. This is called a cusp. It could be that that is the case, why this is undifferentiable. Let's look at the case when x is slightly less than 0, a very small negative number. Well, then this would be a positive value because a small negative number squared. This would be a positive value because this is a, let's consider a small negative number plus 1. This would be positive. And let's consider a small negative number minus 1. This would be a negative number. So we're looking at a negative slope. And then I'm going to put a u, meaning undifferentiable, at 0. And let's see if the slope changes directions or if it keeps going down if we have a small positive value. This one never changes its sign. This one never changes its sign. Now we're considering x to be a small positive value, slightly greater than 0. A small positive value plus 1 is a positive value. A small positive value minus 1 will be a negative value. So this all is going to be negative. So because the sign did not change, we know we're not talking about a cusp. We're talking about some kind of case where at x equals 0 we have an asymptote. And this is a type of function that has a negative slope right before 0, and it has a negative slope right after 0. I'm not saying that this is what this function looks like, but this is a case where there is no local maximum because this infinitely gets to more and more negative infinity. And then as soon as you pass 0, there is no maximum as you get close to 0 from the right. But we know that this is not an extrema. Not an extreme. Okay, so these are the x values where we can say that we found some local extrema using the first derivative test. So the next part was describe intervals where f of x, the original function, is increasing or decreasing. If we want to know if the original function is increasing or decreasing, we should look at the slope of the derivative function. Okay, now we knew that we had found some critical points at -1, 0, and 1. So let's consider these the types of boundary points. Now, let's say on the interval from -infinity until we reach the open-ended boundary to -1. So in this area, let's check the sign of the function by looking at the derivative. This would be a positive number. This would be a positive number. A negative number that is less than -1, so like this would be negative because, say, -2 plus 1, this would be a negative number. And a negative number subtracting 1, this would also be a negative number. So two positive values and will be a positive value. The two negative values would become positive. A positive times a positive is a positive. So we can say that on the interval from negative infinity to negative 1, f of x is increasing. How about from negative 1 to 0? This would be a positive value because of this square. This is squaring something and adding a positive value. This would be positive still. Now, a small negative number plus 1, this would be positive. Small negative number minus 1, this would be negative. Positive, 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 negative. This would be negative. This would be a decreasing interval. How about a small positive, decreasing. How about from 0 to 1? Positive, positive. Small positive value plus 1, this would be positive. A small positive value minus 1, this would be negative. Also decreasing. And from 1 on toward infinity, positive, 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 increasing. Notice how even though negative 1 to 0 open-ended, 0 to 1 open-ended, you might want to write from negative 1 to 1 decreasing and just skip this, but that would be technically wrong. Don't combine these and say from negative 1 to 1, because that looks like you're presuming that the function is defined at x equals 0. But as far as the second part, this part, we can write decreasing we can say negative 1, 0 union with 0, 1. We can say that these are the sets of intervals over which the function is decreasing, this function. You can say it's increasing. What do we have here? From negative infinity to negative 1, the open-ended boundaries. Union with from 1 to infinity, it's increasing again. So far we know it's local maximum and local minimum, decreasing and increasing intervals. Now the next part is to sketch the function. Let's draw a little bit of coordinate axis right here. Let's put a negative 1, a 1 and a negative 1. Let's find out what's the value of the function when x is equal to 1. This would be 1 cubed plus 3 over 1 is 3. So 1 plus 3, this would be, so the value 1,4 would be right there. Now look at this. If x is negative 1, negative 1 cubed is negative 1. 3 over negative 1 is negative 3. So negative 1 plus negative 3 is the same as negative 1 minus 3, which is negative 4. And now let's look at we know that this is going to be a min, so it's not going to go down. It's not going to go down here or here. These places right before and right after 1, 4 are going to be above it. And this at -1, there's a max, so it's not going to go from this way or this way. If you notice this one, let's pay attention to this one for a minute. This one's always going to be a positive value. This one is also going to always be a positive value. And if you just roughly combine them and look at them, if you were to factor in this 3x -2 over this one, if you just combined all these, let me use a computer science term. This would be basically a big O x to the 4th type of family of function. This is a 4th degree polynomial, the mixture of these two, right? And what does a 4th degree polynomial look like? It looks like a very steep parabola-like function, right? And this is always the case, no matter whether you're positive or negative values. So the technique I was using as I was solving this problem, these ones tell you something as far as the sign. This one's like a parabola. And since we know that this is a min, if we draw it like this, that's basically going to be roughly the type of thing that it looks like. And since this is a max, it's going to go something like this. You see how it's never going to have a value at x equals 0. So that's a reasoning with the way that the max and the min that we solved for, the intervals. You see how it's increasing from up all the way until you get to -1, and then it's decreasing, and past 0 it's still decreasing, and then it's increasing on again from 1 to infinity.